Hi everyone. Thank you very much for tuning in and listening to my talk. My name is James Stanfield. I'm a PhD student at the University of Queensland in Australia. And today I'm going to talk about positive Hermitian curvature flow and complex sleep groups. Before I start, I would just want to thank the organizer, Hoju Lee, for setting up this amazing festival. I'm looking forward to watching all the other talks and the discussions that will follow. So thank you very much for the invitation again. And thank you all very much for listening. We'll get started. So the positive Hermitian curvature flow and complex Lie groups. So what this is a generalization of the Richie flow. So what I'm going to do is talk about the Richie flow and the motivations behind this particular flow. So we'll start with the Richie flow, as I said. So let's let M and G be a Riemannian manifold. And then the Richie flow is this PDE. So I'm sure we've all heard of it, but to review, we evolve a Riemannian metric on our manifold in the direction of minus its Ricci tensor. Okay, and this looks locally like a heat equation. So the idea is to smooth out curvature and try to prove things topologically or geometrically. So this has been very widely studied and it's been the main tool in a large number of great results. So for example, when Hamilton first introduced it, he looked at compact 3 manifolds with positive Ricci curvature. And in that case, he showed that such manifolds would be a quotient of the sphere. He also looked at 4 manifolds with positive curvature operator, again compact, and he showed that in that case also they're the quotient of a sphere. The most famous application was by Perelman to prove Thurston's geometrization conjecture, from which followed the long-standing Poincaré conjecture. After that, Boehm and Wilking in 2008 proved a generalization of Hamilton's result. Namely, if an n-dimensional compact manifold has a 2 positive curvature operator, then it's also a spherical space form. And then 1 year later, Brendel and Schoen actually managed to solve the differentiable sphere theorem with this Ricci flow as well. Namely, if your sectional curvature is between +1 and +4, then the manifold has to be homeomorphic or diffeomorphic to a spherical space form again. So given these great results, it's natural to ask if this flow can be used to answer questions in other areas, namely in complex geometry. So I'm going to talk a little bit about complex geometry now to set us up for it. So suppose we have a complex manifold. So what I mean is an even dimensional smooth manifold and an endomorphism or a section of the endomorphism bundle, J, which squares to minus the identity and also solves this analytic or this integrability condition. Equivalently, we can just think of it as an n-dimensional complex manifold. Well, a manifold that admits a holomorphic atlas of charts. Okay, so charts into Cn such that the transitions are holomorphic. But the characterization with the smooth manifold and the complex structure is useful when we want to do geometry. So let's do some geometry. A Riemannian metric on M is called Hermitian if this J respects the metric like this. Okay, so it's a linear isometry on each of the tangent spaces. So fairly natural condition to have on the geometry on a complex manifold. So we can define this thing called the Kähler form. And it's a 2 form, right? So it's fairly easy to prove this, that this would be a 2 form, just showing it's anti-symmetric in the 2 entries. And then we can ask questions about this 2 form. So for example, we can impose that it's closed, and in that case, we call G Kähler, a Kähler metric. This condition is actually just equivalent to the Levi-Civita connection preserving J, for J to be parallel with respect to the Levi-Civita connection. These are much rarer metrics than Hermitian ones. So any complex manifold will admit a Hermitian metric, but Kähler metrics are topologically obstructed. Okay, but they're also very nice in this sense. So on a Kähler manifold, because we have this condition with the Levi-Civita connection, the Ricci curvature operator is actually Hermitian, in the sense that it respects this J as well. So that means that Kähler metrics will be preserved by the Ricci flow. Okay, and this was first observed by Hamilton actually in his original paper. And this yields the very well studied Kähler-Ricci flow, which has been used to a lot of success by a lot of great authors. And there's unfortunately not enough time for me to talk about the amazing properties of the Kähler-Richie flow, but it's quite a beautiful theory. But on the other hand, on a non-Kähler but Hermitian manifold, the Ricci curvature is no longer Hermitian, okay? Which means it no longer satisfies this equality in general. So that means that the Ricci flow will not preserve Hermitian metrics. Which is a problem. So we cannot just blindly apply the Ricci flow to a Hermitian manifold because the metrics won't remain Hermitian, and we can't use it to answer complex geometry questions. So we have to try and construct a new flow that generalizes the Kähler-Richie flow in some sense. So that's where we come in with the Chur connection. So suppose we have a Hermitian manifold. Then the Chur connection is the unique connection nabla satisfying this. So G and J are both parallel. Okay, and then the torsion satisfies this. So remember that the Levi-Civita connection satisfies this. So in our case, the Levi-Civita connection satisfies this. But in this case, we want to make J parallel. Okay, so we choose a new connection so that J is parallel, but we have to give up one of these conditions. Namely, we give up that the torsion vanishes. But the torsion is still nice enough to satisfy this property, and there is a unique connection satisfying this. So we can observe that G is Kähler if and only if the torsion is 0, if and only if this nabla agrees with Levi-Civita. And then the Chur connection, the Chur curvature of the connection is just defined in the same way you would define the Riemannian curvature. So it's this commutator of nablas. Okay, and then from there we can define a Ricci-like tensor, namely the second Chern-Ricci tensor, where we just sort of trace over the first two elements here, the first two entries. I say the second because there are other traces you can take, and they're not all the same because we no longer have the Bianchi identity being satisfied by this connection. The important thing now is that if this Ricci curvature is now Hermitian, okay, and that it respects the complex structure J just like G does. And so this is a very natural candidate to try and flow a Hermitian metric. So indeed, that's what Streets and Tian did. So they introduced this whole family of flows actually called the Hermitian Curvature Flows, which we'll call HCF. So we evolve in the negative direction of this S tensor, and we add on this other term. We modify it a little bit by a quadratic tensor in the torsion. Okay, and the choice of that is free, and that gives a whole family of flows. All of them behave very nicely. So, for example, Streets and Tian showed that it's strictly parabolic. The operator, by that I mean that the operator given by that is strictly elliptic on Hermitian metrics. Okay, and so when we have a parabolic, this strictly parabolic flow, that means there's a unique short-time solution on compact manifolds. Okay, when the initial metric is Kähler, the torsion vanishes, and so this term vanishes, and then this just becomes the Ricci of the Riemannian metric, and so the HCF turns into the Kähler-Ricci flow. So this truly is a generalization. And Streets and Tian was also showed some nice regularity properties and some stability results near Kähler-Einstein metrics under these topological conditions. So already this whole family behaves quite nicely. But of course, the choice of Q depends on what you want to do. So it depends on the application. So there's a few actively being studied. What I'll call the gradient HCF is one where the Q is chosen so that it is the gradient, the HCF is the gradient flow of a certain functional. That was studied originally by Streets and Tian. Another active one, also introduced by Streets and Tian, is the pluriclose condition, the pluriclose flow, sorry, where Q is chosen to preserve the pluriclose condition. So remember, the Kähler condition is that this form is closed. The pluriclose condition is this. Now, of course, any Kähler metric will satisfy this by the DD bar lemma. So this is a weaker condition than B and Kayla, but you can choose Q so that it's preserved, and that's been a very active area of study. And Ustinovsky introduced this flow, the positive HCF, which preserves curvature positivity conditions on Hermitian manifolds. And this is the one we're going to focus on today. So what problems could we answer with this? Well, there's a few outstanding ones. For example, you could try and answer the question of existence of a complex structure on S6. Namely, you could try and contradict the existence of a complex structure on S6 using a Hermitian curvature flow. There's also classification of complex surfaces. So all complex surfaces admit pluriclose metrics, and it's been a very active area to study the pluriclose flow on surfaces to try and maybe gain some understanding in the topological classification of them. There's also uniformization problems with curvature positivity conditions. So like the one I mentioned, like the ones I was mentioning on the second slide about certain curvature positivity conditions giving restrictions on the topology. So one could ask that in Hermitian geometry. So these are just some problems on the horizon that one could look to answering with these flows. So I'll move on and I'll now focus on the positive Hermitian curvature flow. So again, it's just the HCF, but we choose a specific Q. Now that Q is this term. Okay, it seems a little bit meaningless now, but perhaps when we see the application, it will be a little bit more clear why we care about this flow. So Ustinovsky introduced this flow, as I said, and he showed that it preserves what's called Griffith's non-negativity. So the curvature, or the Chur curvature of a Hermitian metric, is Griffith's non-negative if this inequality holds for all x and y in each tangent space. Okay, and as I said, Ustinovsky showed this is preserved under the HCF, which mimics the properties of the Richie flow as well. So as an application of this flow, Ustinovsky was able to show quite a strong result here. Namely, if we have a compact Hermitian manifold with Chur curvature that's Griffith's non-negative everywhere, and strictly Griffith's positive at some point, then this has to be biholomorphic to the complex projective space. Okay, so quite a strong uniformization result coming out of this flow, which makes it quite exciting. So the point of my project was to try and study this flow on spaces with more symmetries to gain an understanding. So Ustinovsky already sort of looked into this and studied the HCF plus on complex homogeneous manifolds with submersion metrics induced by left invariant metrics on G. Okay, so what do I mean? So G is a complex Lie group. Little g is a left invariant Hermitian metric on G. Okay, and by left invariant, what do I mean? I mean that when we pull back by, when we pull back by the left translations, this leaves G invariant. Okay, so remember the left translation is just the map that sends anything to its left translet by X. And so Ustinovsky studied submersion metrics induced by left invariant metrics on the quotient. So what does that mean? Well, I mean that, so we have a left invariant metric on G, and then we have a map to the quotient, which is just a projection. And then G hat is just the unique metric that makes this projection a Hermitian submersion. Okay. And what Ustinovsky showed is that if we have a left invariant solution to the HCF plus on G, then the corresponding submersion metrics will be a solution on the quotient. Okay. And so one can reduce the study of the flow of submersion metrics on the quotient to the study of left invariant metrics on G. So Ustinovsky showed some results relating the growth behavior to the structure of G. In particular, he showed that the maximal existence time is infinity if and only if G is solvable. Okay, so you get immortal solutions if and only if G is solvable, which is quite nice. So maybe I'll just quickly mention some previous work on HCFs with symmetries. So for example, the gradient HCF self-similar solutions were studied by Puja on complex unimodular Lie groups. And then Lafuente, Puja, and Visoni studied the behavior on the behavior of the flow on complex unimodular Lie groups. Namely, they showed long-time existence, and they showed the flow actually converges to a self-similar solution. It was also studied by Pediconi and Puja on complex locally homogeneous surfaces. The pluriclosed flow has been quite active as well. So Henrietti, Fino, and Visoni showed long-time existence on two-step nil manifolds. The behavior on complex homogeneous surfaces was also studied by Voling. And the long-time behavior on two-step manifolds, namely the limiting behavior in that case, and also almost abelian solved manifolds, was studied by Arroyo and Lafuente. For the positive HCF, again, the one we're most concerned about for this talk, Ustinovsky studied it on submersion metrics, as I mentioned before. Pinelli and Podesta studied it on compact C spaces. These are homogeneous spaces which are acted on by a complex semisimple Lie group. And the two-step complex nilpotent case was studied by Puja as well on the HCF plus. So these are some results with symmetries. It's by no means an exhaustive list of what's going on here. I just thought I'd throw these in to show sort of the activity that's going on with the research behind this. So let me get to sort of my main result. So let's suppose we have a simply connected complex Lie group with left invariant Hermitian metric G. Okay, then the let's take the unique left invariant solution to the HCF plus. So why do I say unique here? Because a left invariant solution to the HCF plus is determined by an ODE on the Lie algebra, and standard ODE theory gives us existence and uniqueness immediately, essentially. So the natural question in this case, right, is when G is solvable, which again Ustinovsky showed if and only if T max was infinity, then what is the limiting behavior when we approach infinity after maybe rescaling the metric? So my first main theorem studies this not when G was solvable, but when G is nilpotent. Okay, so a strict subclass of solvable, but still quite general. So I showed that after rescaling by 1 on 1 plus T, then these Hermitian manifolds subconverge to an HCF plus soliton. What do I mean by that? It's a manifold, a Hermitian manifold, that or a solution to the HCF plus, if you like, that evolves only by scaling and pulled back by holomorphisms. Okay, so self-similar solutions to the flow, the geometric fixed points. That was my result. So convergence to a self-similar solution in the nilpotent case. I should mention that the result was already shown by Puja for two-step nilpotent Lie groups, as I mentioned in the previous slide. So I generalized that to n-step nilpotent or k-step nilpotent, if you like. So I'll talk briefly on the proof, and this uses a technique introduced by Lauret and later modified by Boehm and Lafuente called the bracket flow or the gauge bracket flow. So suppose we have a simply connected complex Lie group, and suppose it has a Lie bracket mu on the Lie algebra. Okay, so here, this frac G is the Lie algebra of big G. So suppose we have the HCF plus of left invariant metrics. Well, this is equivalent to an ODE of inner products on the Lie algebra. We just simply push it forward around the whole Lie group to obtain our left invariant solution. So what we can do is for every T, we can write this metric as HT, HT inside of the initial metric here for some matrix HT and GLG. This is not a unique curve of matrices at all, of operators, right? But what we can do is we can choose it such that this So we choose it such that this new mu t, right, this mu t defined by this change of basis action of ht. Okay, so we define this mu t, so this is a time-dependent bracket now, and we choose it so that this time-dependent bracket now solves this autonomous ODE. Okay, now here, there's just some notation going on. This pi a of mu is defined like this. Okay, and this is just the derivative of this action of GLG on the space of brackets. By space of brackets, I mean this this C here. Okay, and then this theta mu is just the operator corresponding to the HCF plus curvature, or the HCF plus evolution term. And then this U, this capital U, is an arbitrary smooth map that takes some bracket and gives a member of the unitary Lie algebra, right? So here U star is minus U. Now the U comes from the fact that I can also write this as being equal to KT HT KT HT, where KT is in the unitary group of where KT is in the unitary group with respect to this metric. Okay, what does that mean? That means that KT star equals, well, it means precisely that KT inside this inner product preserves it. Okay, and because I can choose KT arbitrarily, I can essentially choose this smooth map U arbitrarily as well. The reason we want that is because we want to simplify analysis later on. So basically what we do is we reduce the HCF plus to studying this ODE of Lie brackets. Now, as I said, the HCF plus is equivalent to the bracket flow up to pullback by equivariant biholomorphism. Okay, so it suffices to study this ODE. Now, the proof in the nilpotent case was as follows. Or the idea was as follows. So suppose we have a k-step nilpotent complex Lie group, and we have a left invariant Hermitian metric. And then we consider the bracket flow on the Lie algebra, which again is equivalent to the HCF plus. So the goal is to show this subconverges to a scale static solution of the bracket flow. So what I mean by scale static, I mean some solution such that, say, nu t dot equals lambda nu t. Okay, after some normalization. So once we show it converges to a scale static solution, then we're done, because scale static solutions give rise to solitons in the original setting. Okay, so this is the advantage of the bracket flow, is it allows us to detect solitons, whereas in the flow of metrics, it was harder to see that. Okay, so how do we go about this? Well, we use induction. Okay, so we choose U such that the center of our brackets are preserved. Okay, so this is nothing but the center. And then we consider nu t defined as follows. So we restrict to the orthogonal complement of the center, and we also project onto it. Okay, so we can essentially write mu t as nu t plus eta t, where nu t maps from the orthogonal complement to the orthogonal complement, and eta t maps from the same place but to the center. Okay, so we can observe that nu t is now k minus 1 step nilpotent on the orthogonal complement, or on the quotient by the center. Okay, and then the key part about the HCF plus is that this actually solves the bracket flow equation. Okay, now the other part, eta t, is 2-step nilpotent, which intuitively is going to be a little bit easier to deal with. Okay, but the key thing is that the k minus 1 step nilpotent part also solves the bracket flow equation. So this leads to the idea of using induction on k. Now the question is, what is the base case? Well, that was treated by Puglia, as I mentioned. So that is sort of an overview of the proof. So what we did then, we have to choose a monotone quantity that behaves well with respect to this induction, which lets us prove subconvergence. And barring a few technical details, that's the spirit of the proof. So my next result answered this so I'd already answered it on nilpotent Lie groups. Now the question is, can we answer it on solvable Lie groups? I think it's probably out of reach in the full solvable case. But we could answer it on a special class of them, namely the almost abelian ones. So a complex Lie group is called almost abelian if it has a codimension 1 abelian ideal. Namely, if I can write its Lie algebra, if its Lie algebra has a codimension 1 abelian ideal, namely I can write its Lie algebra as this semi-direct product here for some matrix A. Okay, so there's an n-dimensional abelian part and then a one-dimensional part that acts by a matrix with the bracket. Okay, so my next theorem was that if G is non-nilpotent but almost abelian, then again we get convergence in the Cheeger-Gromov sense to a soliton. Okay, now the proof is pretty neat. The bracket flow in this case just reduces to this flow of matrices. Okay, and then we just need to find a monotone quantity that gives us what we want. So what we can do is define the Frobenius norm of a matrix A like this. Note that we also have a Frobenius inner product like this. Okay, and then we want to use this to define a monotone quantity. It's exactly what you think, actually. So if we differentiate the norm of A, or the norm squared, this gives us twice of this. Okay, so we just put, so this is just A dot A star. Okay, and then expanding this out and then using the Cauchy-Schwarz inequality, we get that this is actually, it's non-increasing. Okay, and it's stationary, right? So equality holds if and only if this is some multiple of A star A, or AA star is a multiple of A star A, which actually happens if and only if A is normal. Okay, but if A is normal, that means that that A is not moving. Okay, in particular, A dot is some scalar multiple of A, namely when lambda equals 0. So A is a steady soliton. Okay, so we get convergence quite easily to a steady soliton in this case. Okay, and the reason I have to say non-nilpotent here is because the matrix ends up being normal. Okay, so we need it to remain non-zero. If the matrix is going to 0, then we have to rescale. So you can see I have not had to rescale here. So that's why we say non-nilpotent, but the nilpotent case is covered by my other theorem. All right. So in this case, in the almost abelian setting, again, we can classify solitons or self-similar solutions. So if we have an almost abelian complex Lie group, then, so this is parameterized by some matrix A, then it admits a left invariant soliton if and only if this matrix is semisimple or complex diagonalizable or nilpotent. And moreover, any such soliton is actually unique. So A is either this up to conjugacy, or it's this. So it's either strictly upper triangular essentially, or strictly diagonal. No mix of those two. And that's the only time that such a group will admit a left invariant soliton. Okay. And the good thing about this proof is that it's constructive. And so this actually gives many explicit examples of homogeneous HCF plus solitons in all dimensions, which previously weren't known. I should mention that all the nilpotent examples admit compact quotients. And that's simply due to the fact that we can write A in Jordan canonical form as basically a strictly upper triangular matrix with only ones above the diagonal, which are all rational. And Lie groups, nilpotent Lie groups with rational structure constants admit quotients by a theorem of Malsev. So that wraps up my results for the solvable case. And then a natural question is what happens when it's, say, semisimple, when the group is semisimple, i.e. when the maximal existence time is not infinity. So if we have a semisimple complex Lie group, there's a canonical left invariant metric that actually comes from the killing form, okay? And we get that by writing the Cartan decomposition and then finding the Cartan involution and composing with the killing form to give us a positive definite inner product. So this gives us a canonical static metric on each of these on these complex Lie groups, the semi-simple ones, I mean. These are the direct analogs of Einstein metrics from the Riemannian case. So there's a natural question: does any left invariant HCF plus solution converge to this canonical metric? In fact, the answer is not true. So what I showed is when we just take SLNC for n greater than or equal to 3, then this metric is actually locally unstable, right? So there exist solutions to the HCF plus beginning arbitrarily close to G sub k, but they don't converge to it. Okay, so it sort of looks like this. So you've kind of got, well, I should say that I proved this using a 3-dimensional subspace of add SLN minus 1 invariant metrics. Okay, so 3-dimensional subspace, but after normalizing, we get a 2-dimensional family. Okay, and so we can study the phase plane or the phase plot, and this is G sub k in this instance, and it sort of looks like this. We've got solutions coming in here, and in here, but we've got this unstable part which actually converges to here. Okay, and that's actually a non-trivial soliton that it converges to. And this disproves the conjecture of Ustinovsky regarding the limiting behavior on simple Lie groups. So unfortunately, the flow is not as well behaved as we might expect in the semi-simple case or the simple case, but still quite well behaved in the solvable and nilpotent case, clearly. So that is pretty much me, I think. So we'll leave it there. Here are some references that I will just cycle through, and you can pause the video if you want to look at them more closely. But again, thank you for listening to my talk, and thank you for the organizer, Hoju Lee, for the opportunity to speak. I'm looking forward to answering any questions that some might have, and to see all the other talks as well. Thank you very much, and have a good day.